behind there. All right. So quick announcement before we start. The tutorial, as you probably know, is due coming up on Wednesday. Not the tutorial itself, sorry, a check-in for the tutorial. This is a sort of a very quick, it's meant to be a quick check-in. One thing I did post yesterday, or last night, I just sent a notice out about, is that I put a lot more information on the tutorial on the webpage. So it's a much more detailed write-up now with a little bit more about the criteria for what we're looking for in the grading, as well as the rubric you're going to use when you grade each other's assignments, because you're going to doing that for 2 others. And so that includes both sort of what you're aiming to do and then what you're going to evaluate in the other tutorials themselves. It also contains a breakdown of the actual grades you're going to get. So this actually will relate to the check-in as well, but the grading is going to be 10% from the proposal and the check-in, 20% based upon, this is not adding up right now. Okay, I'm misremembering it. Maybe I don't even add up correctly, but the vast majority is going to be from instructor evaluation. 20% will be from student evaluation and 10% from sort of basic check-ins. The other 10% is just doing the evaluation as well. So you have to do it. You get some credit towards it, but it's just basically a check of whether you do a good job because you're doing this for other people. But it's mainly a check of whether or not you're actually submitting something for other people's as well. And I think 60% of the grade will be just the instructors evaluating the tutorials as on the same scale as everyone else's. So a few notes on that. First of all, the check-in is due this Wednesday. Remember, that's going to be it's approximately half the size of the final tutorial, so it has to be at least 500 words, and at least, which is not very much, incidentally. So it's actually, you could do more. You could do it to all 2,000 if you want, but it's at least 500 words, and then at least 50 lines of code. And that's more or less just to kind of get people working on these things. We're not trying to force people to do too much for the deadline, and it's due Wednesday. We're not going to have, a lot of people have asked for extensions on this one. We're not going to grant extensions except for the normal kind of extenuating circumstances outside of coursework. Just having a lot of midterms and stuff doesn't get an extension. But you should, and you can use late days, but you should check the grade breakdown before you use those. In particular, the check-in counts for 7% of your total final grade. So don't stress out too much about it. Try to get something there, and mainly it's sort of a check to see whether you're submitting something or not, where we'll decide what's reasonable. But don't worry too much about that. I would probably recommend you don't use the late days for that. I'd recommend you use them for something a little bit more, larger impact on your final grade. Secondly, we've moved some of the dates around. There were some comments, I think rightly so, that it was a little bit close to the 4th homework being due, the tutorial being due. So we pushed it to the Wednesday instead of the Monday, which it was going to be. So it's going to be now Wednesday, the 2nd of November. And the other thing we changed is you actually can use late days now. So before we said no late days, now we're saying you can use up to 2 late days. The flip side of that is you now have less time to evaluate each other's tutorials, but it seems like that actually takes much less time, I think, than actually doing it yourself. So you have a little bit less time to evaluate now. That's due the following Wednesday. So you have not quite a full week to do that, but hopefully there'll be plenty of time for everyone to get stuff done. Lastly, they have a lot of questions about switching topics. So which is not surprising. So it probably was happening. People are working on these things. They're realizing the original topic wasn't that interesting or just too broad for the scope of what we're covering here. So you may switch topics. Ideally, you're actually sort of narrowing into a subtopic of what you proposed originally. That would be best, maybe. But you don't have to. You can, if you really want to, switch entirely. Just know that we can't give you feedback. We cannot guarantee we're going to give you feedback on your switched topic. So that may prevent you from having as good a topic as you would hope. But you can do that. You even can do it after the check-in, maybe, but I wouldn't recommend that. You put a lot of effort in the check-in, so don't do that unless you really need to for some reason. But we're pretty flexible there. You don't need permission necessarily. If you want to run it by us, that's fine, but hopefully that sort of covers most people's questions, I think, about the logistics of the tutorial. Question? Yeah, what we're going to do is we're going to make them all available to everyone, but we're going to assign you everyone two random, I mean, 2-1 so that everyone gets reviewed by 2 other people. So we're going to assign a matching to everyone randomly. Yes, so you will be assigned, but you also can look at others. You don't have to provide feedback for others, but if just seeing 2 isn't necessarily a lot to sort of situate how am I supposed to grade these things. So you can look at others if you want to. Look at other topics, of course, if you are interested in the other topics. But the goal will be for you to only provide written feedback for 2, which you are randomly assigned. Okay. All right, so today I changed the schedule a little bit. And I think this is going to happen a few more times as we go on. In an effort to cover everything, I think we need to do a little bit more justice to probability and statistics. And so I chopped out the lecture for now on data imputation. We may come back to that a little bit when we talk about anomaly detection, because actually these are very similar things. Data imputation, which means filling in missing values of data and preparing your data, and anomaly detection, actually, there's a really close connection there. But for the most part, I think we're going to skip that in to favor a longer lecture on probability, just because I think these are topics that people need to. They're kind of foundational to a lot of data science, and we want to cover them in depth. And I also want to get to naive Bayes for sure by this Wednesday, so you have that covered for your homework. So before we do that, though, I need to finish up from last time where we were talking about nonlinear classification. And when we ended last time, I was kind of rushing through a little bit, talking about some of the radial basis function methods that we had discussed so far in class. So the idea of radial basis functions is they are another general kind of nonlinear feature you can construct from your data. And kind of like polynomials, but of a different category, right? Instead of sort of being these sort of instead of being polynomial functions of your inputs, they are kind of weighted sums around certain points in your, or weighted exponentials around certain points in your data, and you define features basically on how far you are from a certain point. You take the exponential of that, negative exponential of that, and that becomes your feature. And just to clarify here. The rule we talked about really for this was this one. So this was the RBF feature, where you take your input x, you take a bunch of centers, mu I, divide by 2 times this bandwidth parameter squared, and those become your new features of your data. And one thing I sort of suggested as an algorithm which you should always try, it doesn't always work, but it typically works pretty well, is that instead of trying to cover your entire space with a grid of centers, just pick your centers at random from your data itself. Or if you want to be fancier, actually pick them through the k-means algorithm, which we'll cover in a few weeks. And then pick the bandwidth not through some fancy thing, but through this thing called the median trick, which kind of picks a reasonable parameter in a lot of cases. So this is always the second algorithm I try, I should say, on most data sets, unless there's a really good reason not to try this one. The first one being a linear model. After I try a linear model, I will almost always try this algorithm to see if there's substantial nonlinear characterizations there. Now, I'll talk a little bit more kind of throughout the course on kind of the whole data science process, but one of the processes I use is first linear methods and then this RBF with centers placed around the data points. And what it looks like, what these features look like are essentially, they look like smooth functions over the raw input space. So if our raw input space is what I'm plotting here. So this is our cancer data set. I'm showing the mean area of the pixels on the x, mean number of concave points on the right. And this is actually not bad to describe with a linear function here, but you can do a little better if you use nonlinear functions. And what I'm showing now is different parameters of radial basis functions. Just like with different polynomials, you have different fits to the data. You can do a similar thing with the radial basis functions. And so here is a evenly spaced grid of 3 along each axis. Here's an evenly spaced grid of 10 along each axis. and here's an evenly spaced grid of 20 along each axis. So you can see here we're starting to probably overfit this data, right? Because we're getting these little bumps in the space that are classifying this region as being positive and this region as being negative right next to it, and there's probably no reason for that. It's just fitting precisely to the data that we actually have here. Now, importantly though, when it comes to radial basis functions, there are a few other tools we have or levers we have to tune the complexity of the model, right? So for polynomials, we sort of had two ways of increasing or decreasing the complexity of the polynomial, right? We could either add more or less polynomials, right? We can control the degree of the polynomial. And secondly, we could control the bandwidth. Sorry, I'm skipping to this slide here. Secondly, we could control the regularization parameter, this lambda parameter. Greater lambda means a less complex model, and lower lambda means a more complex model. Well, for RBFs, we can do the same thing, all right? So if we can just increase the raw number or decrease the raw number of them, that's number one. That's like adding or subtracting polynomials, or adding more or fewer polynomials. We can also increase or decrease the regularization parameter, but we actually also had this lever of increasing or decreasing the bandwidth parameter, this sigma parameter, that also controls complexity. And so the way to see this, and I apologize for skipping around a little bit here, but the way to see this is that in the case that we choose sigma very small, that means that we essentially are letting the function vary very heavily between neighboring points, right? Because if we have sigma varying very small, then 2 points that are very close to each other will still have very different features. Whereas if we have sigma being big, then 2 points close to each other actually have to have very similar features. And that's a little bit not that easy to see, maybe. But the extreme case to take here is that if we have, so x j here is going to be equal to x minus mu j squared negative over 2 sigma squared, right? So if we have this for two different j's, as sigma becomes infinite, right? As sigma becomes infinite, then all these terms will actually go to 1, right? Because it doesn't matter how far apart these two terms are. As we get a bigger and bigger bandwidth here, this whole thing will be 0 inside this term here, so the exponential of it will be 1. Right? So as our bandwidth becomes bigger and bigger, we essentially approach a constant function, and all we can represent is the constant function. As we get sigma smaller and smaller, we have functions where, you know, maybe there's one, and I'm going to use say 1 here, and then we have also x2 j. Actually, I should more show it like this. Let me use that notation there. Where's the eraser? There it is. So sorry, let me use phi here because I was using that in just this section of the notes. Of course, I been rewriting new notes now, so I went back to my old notation. And this is actually a 2 norm here, emphasizing the fact that these can actually be vector valued. So yeah, that's still j. So let's think about x1 and x2 here. Okay, so let's think about x1 and x2 here. If sigma is really small, then even if x1 and x2 are very close together, we can still have very different feature values at those 2 points, right? Because this term will essentially be small. For this being very, very small, this whole term will be very large for x1 being at all very far from mu j. And so this thing will essentially go, you know, these features there go to 0 pretty quickly as x gets farther away from mu. And what this means is that two different points, so two different data points, x1 and x2, can actually have very different values of their features, even if they're relatively close together, right? Whereas if they have, if you have sort of a very big bandwidth there, you have to have these 2 points very far apart before they have substantially different values for their features. So it's a little bit, it takes a little bit of sort of playing with to sort of get that intuition right. But that's the basic idea, is that sigma here, if you have sigma be lower, that encodes a more complex function, whereas sigma being higher encodes a less complex function. So that's the high level to take away. If any of the other stuff I sort of mentioned about kind of the value of these things and how close these 2 points are, if that made sense, that's great. But if not, just keep in mind the main point here being that sigma is another way we can tune the complexity, and sigma small means complex, and sigma big means not very complex. Yeah?
So when sigma goes very small, points that are relatively far away from your center, those are actually, like, those should have very high.
Yeah, so
So it's really points that are near to the center are going to have relatively different values.
so let's look at it like this, right? So if these 2 points, and I'm just going to think about this sort of j term there, right? So the plot of this function as a function of x here looks something like this, right? So it peaks around, that's supposed to be the peak there. It peaks around that and then tails off very rapidly in a bell-shaped curve. And so if as the bandwidth increases, or decreases, sorry, this peak here gets more and more narrow. And so these points have less and less in common. I should say, at some point, they're all just kind of 0. But I'm assuming that there are some features that are actually different. There's enough features here that they each have, some mean, some value that's not just all zeros. So they're all zeros, and that's a pretty boring function. You're not going to capture very much. But assuming that we have enough centers such that there's at least one center here for each point that is reasonably close enough to have a non-negligible value here, what that means is that the actual features, right, will have very little overlap, because maybe this guy will be big for x2 and some other guy will be big for x1. So the features won't really overlap. Whereas if this is getting bigger and bigger, then this one for x2 and this one for x1 have to be kind of similar, because x1 and x2 are similar. And the way to see this, by the way, is that ultimately our final, and this plot should probably actually, maybe I'll add this plot to the slides. It's too late now, but oh well. The final function, remember, is going to be, our final function we're approximating is going to be a linear combination of these functions, right? So it's basically going to be, theta 1 times this plus theta 2 times this. Could be positive or negative, so we can have sort of negative things or positive things. And then theta 3 times this one, right? We add these all up, and that's our final approximation. So when these things get sort of narrower and narrower, you have a function that can vary a lot more rapidly, right? Because it can sort of have these sort of heavy slopes here. Whereas if you have a function like this, if our bell curve looked like this, then the function that you would get from adding these things up actually couldn't vary that quickly over different points in your space. So this is actually fairly kind of advanced when it comes to machine learning. RBFs are they're very common, but they're quite powerful, and you can kind of do a lot with them. So hopefully it kind of makes a little bit of sense. I think the best way, honestly, to kind of get familiar with this is to play around with them. So in your own data analysis, I would really heavily recommend using these things. Not just through scikit-learn, because they're really easy. There's, I actually had a typo in my slides last time on the RBF function, but now it's fixed. So download the latest one and then play around with it. It's a really useful type of generic feature. One of the more useful ones. Does not have the power of something like a deep neural network, certainly, but it's much easier to get going, and it's much easier to sort of quickly try out. So I'd really sort of highly recommend trying it out. Okay, so then the last thing I'll say is that we have these other levers, right? We have these levers of number of RBFs, the raw number, more means more complex. We have the regularization, less regularization means more complex. And then we have the bandwidth, lower bandwidth means more complex. And so what I'm going to show now is the same sort of figure, still with a grid of 20 radial basis functions per dimension. So it's actually a 400 center grid here over this entire space. And I'm going to increase the regularization parameter. So here it is with sigma equals 0.1. We have these big kind of quickly varying regions where this is positive and this is all negative here. If sigma equals 0.5, we have this. So it's still kind of heavily varying, but much less so than the one before. We no longer sort of have that little region there. We have a much smoother function. And as I increase more, we have smoother and smoother functions. So this is again, still 400 radial basis functions covering this space, but a higher bandwidth to make them not quite so prone to overfitting. This is actually the sigma you get. It's about 1. This is the one you get from the median trick. So if you use that distance between them, you'll get this parameter. And then finally, if you go ahead and just use RBFs based upon the data, you'll get this plot here, which is actually also pretty nice and smooth around this area. It captures things pretty well. Don't worry too much about this space over here. What's actually happening over here is the function's almost 0 over there. So it happens to be a little bit less than 1 just because it has to pick, or sorry, less than 0 because it has to pick one or the other. But really, what's happening here is that we're just very unconfident in our prediction. And so, the color there doesn't really matter. But just a kind of an aside. OK, so any questions on that? I'm going to switch topics then. Hopefully we'll get to some probability today. Really want to. All right. So let me talk now two relatively quick things that kind of finish up a miscellany of topics here related to nonlinear models, overfitting, training, testing, and then also evaluation. So I'm going to talk now about evaluating machine learning algorithms. And I want to start this by saying, kind of giving a common procedure. And everyone also, by the way, knows in class this is why this is incorrect, or most people do at least. But then they do it themselves anyway. And I'm not unguilty of that as well. I'll fully admit. Maybe not of reporting at this, not quite this bad, but I'll actually talk about what I'm guilty of later on in these slides. So here's a very common procedure, right? You want to know how your algorithm is going to generalize to new data, right? You don't want to just report your training error as the performance of your algorithm. That would be very clearly a bad thing to do. You'd say that a polynomial 50 function is great at fitting your data. So what I'm going to do instead is I'm going to separate my data into training and a cross-validation set. I'm going to try different algorithms, different parameters, different regularization, et cetera, on the different, with many different parameters, train it on the training set and evaluate it on the cross-validation set, on the holdout set, right? And then I'm going to take all of those. I'm going to look for the best one. Maybe my best cross-validation holdout loss is something. And I'm going to report that as the performance of the algorithm, of the best algorithm, right? So this is somewhat common, actually. And what's wrong with this as a question, though? Yeah?
Because actually, when we use our cross-validation set to check which algorithm is the best, we actually use these points again and again. And so we actually train in our algorithm on this set.
Yeah, that's the base. That's exactly right. So the problem with this is that we are essentially we may be starting to overfit to the validation set. Because even though we're using the training set to train our parameters, the thetas, right, we're actually here using the validation set to train our hyperparameters in a certain sense, right? We're picking the best set of hyperparameters on this holdout set. So here's sort of an obvious example that's clearly wrong, but actually is reasonable. So imagine an algorithm that just ignored the training set and generated random predictions on the cross-validation set, right? If you run enough of those, you will get some algorithm that gets the validation set perfectly right, because you'll eventually get one that predicts it correctly. That would not be a very good measure of the performance of this random prediction algorithm. You've just used it to essentially you've just used the hyperparameters to effectively train and fit to the holdout set. Now, of course, when you have only one hyperparameter, just say lambda, like your regularization parameter, this is less likely to happen. You probably won't do this, but this methodology still is not correct, so you should not use it. You should use something else instead. Does that make sense to everyone? Yeah. So I'll get to that in a second. So I won't repeat the question because I think I'm going to have it on the next slide. So what's the right way to do this then? So the right way to do it is the following. Right? So the right way to do it is to separate your data into 3 sets. The first is the training set, and you're going to use that to train the parameters, to learn the thetas. The second set is the holdout set, the validation set. And the third set's called the test set. And I've avoided using the word test set because I want to be very specific about validation and cross-validation not being the same as a test set. So the idea is we're going to train the algorithm on the training set to learn the parameters, and then we're going to fit the hyperparameters by optimizing over the validation set, the holdout set. Right? So I'm going to pick, say, my regularization by drawing this figure. Find it again. I have so many slides in this deck here. So I'm going to draw this figure on where this is my holdout set, and the blue bar is my training loss. The red line is my red line. The green line is my holdout error. I'm going to use that to predict. I want to pick this point here because that looks like the best setting of my hyperparameters. In this case, my regularization parameter. And then I'm going to finally evaluate the whole thing on some separate set called the test set, which I haven't looked at all before. Okay? And then, this is what everyone is guilty of, and I actually would challenge people to ever not do this. Then you do this once, you look at your test set once, you get one number, and if it's bad, you abandon the whole project because you've now corrupted this test set forever, and you can never test on it again. You can also optionally within there also, if you really want to, you can also retrain on all your training and holdout set, because it can actually, if you want to use a little bit more data than just your 50%, you can actually use the validation set for training your final classifier too. But then you evaluate your test set, and if it's bad, you throw away your results, and you never speak of the project again. Of course, this is not what people do, right? People, if after testing things out, you turn your test set and you find you actually did overfit to your data, you're not going to just abandon everything. You're going to try to redo something. And that's the subtle way in which this same exact problem creeps in to actual kind of scientific work, right? People make implicit kind of decisions based upon those few tests they do on their holdouts, on their true test set, and that biases their whole results. Now, here's what you can do kind of to stop that. And I call this kind of leakage of the test set performance, right? Because it's very, very easy and very tempting to evaluate test set performance. That's what you can actually include in your paper, right? You don't want to have a big XX unknown in your paper before the deadline and then just finally plug it in, right? You're going to evaluate it. And so how do you prevent this from happening? How do you prevent leakage of the test set into your implicit sort of choice of algorithm and choice of design of your entire problem? Was there a question there?
So in the previous slide, if you separate the data set into these 3 parts, which data set would you look into to reconfigure your features?
Okay, so the question was, if you're doing this, which data set would you look into to reconfigure features? To reconfigure your features? That's a great question. So the choice of features for an algorithm should be thought of as a hyperparameter of that algorithm, right? So the way you choose your features is you train them, you pick some set of features, you train them, you find the best classifier for those features using the training set, and then evaluate the performance of that classifier on the holdout set. So you're using the holdout set really to evaluate how good those features are. So when you say okay, the question, what do you mean by you need to look into those data?
For example, in text mining, you need
Right. So yeah.
Find certain patterns.
Okay, right. So the question is sort of what data should you be looking at in your feature engineering process? So far I'm talking kind of more about kind of generic features you can build, in which case you're, yes, you want to be looking at the data, but you want to be looking at the performance.
Algorithm by
Yeah.
the performance, right?
Right. So when you are looking into the data, and as you should when you want to visualize the data, when you want to pick features to design. I talked about polynomial features, which you may need some expert knowledge in order to pick the best set of features. That has to be done really on the training set and maybe the holdout set. I mean, depending kind of on where you lie in between the.
Actually, looking into that data set is kind of biased. Right?
So the question is, if you look into the data set, is it kind of biased? So it is absolutely true that if you use the holdout set to design your features, you may bias yourself towards that holdout set. So why not add a development data set at the very beginning? You can, but the problem is you may as well just use the training set. If you're really that kind of worried about it, just use the training set then. I think you actually can use the holdout set because, you can use the holdout set because you still have this test set as the ultimate metric of your success. So you should be, as much as possible, you should be clearly doing things that you don't believe will overfit to the holdout set. You should not be designing, the random features that happen to do well on that one holdout set. But you do have this guard, and you will have this ability to actually evaluate the true performance of the algorithm on some new, truly previously unseen data if you have this test set available too, right? The other little odd thing that, is something you actually should think about is it okay to look at the data, the X's, the raw inputs, if you don't look at the labels you're trying to predict? And in some cases, that actually is okay. In some cases, depending on your setup, you can look at the actual inputs on all of your data. If you always assume that you're going to have the inputs before you make a prediction, I'm going to be able to do a reanalysis every time I get a new input, then it's absolutely fine to look at all your inputs, right? You just can't look at the outputs. You can't look at the Y's on your test set. So you can look actually at the inputs. You can design your features looking at the inputs. So it really kind of does depend a little bit on the domain. The flip side of that is if you have to develop a system that will operate online, where you won't have the ability to retrain after seeing a new input, you probably don't want to do that because you won't be able to then adapt to sort of changes in your distribution over new inputs. But there are subtleties here that sort of are very important in sort of the development of your whole pipeline of process, right? I guess the short answer though is that in developing your algorithm, if you want to use a separate data set, fine, but you typically don't have an infinite amount of data, so it's you're better off using all the data you have available, creating a training set and a holdout set, doing all your development with some combination of those two sets, and then having this final holdout test set. And again, I'll get to kind of the practical implications of this, but the best way to sort of prevent eventual leakage of the test set into your design of your algorithm is to do a few things. And this is actually possible to do, and these are sort of best practices you really should do that strike a reasonable balance between that ideal of just throwing everything away because you've corrupted your data once you've tested once on the test set, and the reality where people just sort of overfit the test sets frequently. And to that sense, I'll give kind of a few prescriptions about what you can do. So the first thing is, if you are developing a system that will be kind of evaluated in the wild, if it will be somehow used as a part of some larger system in practice, then try to use it in that system. Try to use it in the full pipeline in the way it's actually going to be used. And this seems obvious, but it actually is not always done in practice, right? People spend so much time looking at a little slice of their problem, they don't actually evaluate the thing in the context of the larger system it's being used in. So first of all, if if you are going to use it in some sort of real in some actual system, use it there. And that often will sort of point out errors you made in your implicit errors you made in your construction of your test set. Maybe you did use maybe you did design features that were really biased towards your data, and so they worked great even on your test set. But all of a sudden you plug it in, and the features are nothing like they actually were. This is very common, by the way, when people when you pull data from some website that sort of filled in missing values in the past based upon future outcomes, right? So you've built some data set that you built some classifier on some data set where there's been actually kind of you're trying to predict some sort of future event from past data, and in the data you're querying, there's some unknown flag in your past data that actually kind of gives away the answer. So everything looks great in the test set, everything looks good in cross-validation. But then when you actually run it in the system in the wild, it just fails completely because in the true nature of the data, you don't have that information. So evaluate in the wild as often as possible. That's number one. Number two is you can get around. You don't actually have to throw away all your data. You can get around this by collecting more data, right? You can always collect more data from the same source that you got your original data from, and that's also going to be a new valid test set. And so you can kind of, effectively repeat the process of having more and more test sets, and you layer these things, so you sort of try to use them less and less. Look at this sort of peek under the curtain here very sparingly. Try to do everything in cross-validation until you really believe your performance of your algorithm is good, and then evaluate what's in your test set, kind of to check to make sure you did nothing wrong more than anything else. And if you did do something wrong, go back and reevaluate. So collect more data, look at test set sparingly, and try to evaluate the system in the wild. I mean, in the wild is really the best thing because that really is doing both those things. It is collecting new data, and it is only looking at data once you definitely don't have the answer to. That's, of course, sometimes easier said than done, right? Because someone's data is very expensive, or if it's a temporal thing, it may take years to collect new data. So you may not be able to do this. And you have to figure out ways around this and figure out ways where you really can try to build models that do not overfit to something that you are trying to keep as a holdout blind set. The last thing I'll say is that there's some really actually very recent and really interesting active research in this area in a technique called adaptive data analysis. And this field essentially looks at techniques from an algorithm or a set of techniques called differential privacy to actually ensure that you're not going to overfit to a holdout set. So what it basically does, and I won't get into this at all because this is just Google that keyword if you're curious about this. The idea here is you actually want to answer queries about a holdout set which are corrected by some noise. And you can prove that if you only ask a certain amount of these queries, you are guaranteed not to because there's additive noise, you're actually guaranteed not to overfit to that data, even if you use an adaptive process where you're looking, using the results of the feedback to pick another algorithm and using that to pick a new algorithm, et cetera, you're actually still guaranteed not to overfit. Now, this is largely still a theoretical interest, but it's one of the sort of these areas I actually think that I think has the potential to actually be quite practical. So maybe that'll become a thing in the next few years. All right, so we're running a little bit behind here, so I do probably want to move on. And I'll finish by talking a little bit about, this is a little bit of an aside here, but I want to mention it here because it is very important in data science, and kind of you need to say this at some point. This is some mention of other classification metrics. So we've been using so far 0-1 loss when we talk about classification. How many, as kind of the true accuracy we care about, right? How many things did you get right? How many things did you get wrong? But when the number of classes is not the same, or if the cost of making a mistake, if you classify something as positive when it's negative versus negative when it's positive, as you might imagine there would be in a lot of domains, if these costs are very different, then oftentimes accuracy is a really bad metric. A great example is, if you're building a spam classifier, and in the current day and age, probably you don't even see it, but probably 90% of all mail is spam at this point, right? If you just, fortunately we don't see it because classification is actually great. But if you just classify, if you just take kind of raw email, build a classifier, and always predict that everything is spam, you'll get 90% accuracy, which sounds great, right? 90% accuracy, that's really good. But of course, it's completely useless because it will throw away all the email you get, right? You won't get any email, so it's not a very good spam classifier. So because of this, in classification, there's often more subtle analysis that kind of looks at the trade-off between classifying some things as positive and some things as negative. So the starting point for this is what's called the confusion matrix. And so confusion matrix says, for all the data points I have, and by the way, all these can be done, all these sort of metrics I'm going to talk about here can be done on the training set or the test set or a holdout set. I'm going to think of them just in terms of a training set, but you can do it on whatever set you want. Just from simplicity, I'm just going to talk about it on a training set, but it's all the same. So you can create what's called a confusion matrix, which basically lists for the examples that are actually positive, how many did you say was positive? For the ones that are actually positive, how many did you say was negative? This is something called a false negative. For the ones that were actually negative, how many did you predict were positive? That's called a false positive. And then for the ones that were negative, how many did you predict was negative? That's a true negative. And so those 4 quadrants, we're actually going to see a lot, and we're going to see them again when we talk about hypothesis testing. We're going to see sort of how we use those things. And here's the one line of a scikit-learn code to actually build this confusion matrix here. Now from this matrix, we can actually also derive a lot of quantities, which are of great importance to different domains. So you may have heard of some of these before. There are actually a lot more. If you look at any one of these things, and people define 1 minus these things, and all sorts of different scores. There's however many elements there are in this matrix essentially. Whatever, one can be the numerator, one can be the denominator, and you have all possible combinations. But here are some of the more common ones. So true positive rate, which is also something called recall, is the number of true positives over the number of total positives. And by the way, total positives, that's total actual positives. Total actual positives are true positives plus false negatives, right? False negatives are things that are actually positive, but you call it negative. And so the number of total positives is the number of true positive plus false negatives. So true positive rate, or recall, is saying of the total number of things that really are positive, how many did I classify as being positive? Now, very importantly here, as a main point, is that these metrics require that we define one class to be positive and one class to be negative in classification. So it's no longer symmetric. And in fact, in our labels, I called one positive and 1 plus 1 and 1 minus 1. So hopefully it's apparent. But the meaning here is actually very different, of course, depending on which class you call which. So if I called my malignant tumor class positive, that has a different sort of set of semantics than if I call my malignant class negative. That would mean different things for what I mean by this. But usually, in most classification tasks, there's kind of a natural setting. So I would typically think that you would say a malignant tumor was a positive example because you were trying to find bad malignant tumors. Or if I was classifying email, I would say that a spam email was a positive example if my goal is to find spam emails. Maybe that's not true anymore because maybe all email is spam. So you're trying to find the actual ones that are not spam. But just be aware that, of course, these things, they're not all symmetric. So they depend on which class you define to be the positive one. There's also the converse of that, which is false positive rate. That's the number of false positives over the number of total false examples there are, or negative examples there are. False positives over the number of total examples there are. Again, over the same denominator. And then the total number of positive examples there are. So that's 1 minus the true positive rate. Wait, no, is that? No, sorry, never mind. That is the number of false positives over this thing. Take that back. It's not 1 minus that. And then there are also things like called precision or recall. We already saw over there. There's many, many more. Precision is a particularly important one. Precision is the true positives over the true positives plus the false positives. So this says, of the total things that I called positive in my data set, how many were actually positive? And again, I don't expect you to actually intuit these things right now because they're actually very unintuitive, and I have to frequently go back myself for a new domain and kind of like remind myself what these things actually mean in that domain. But just know kind of the definitions here in terms of sort of where you can find the definitions and have some sense of how they all relate to the entries in this confusion matrix. And then finally, accuracy is just equal to the total number of true positives plus true negatives over everything that you have there. OK, so that was very quick, but are there any fast questions here? The reality is that most domains have their own metrics that have become important for whatever reason, and they use those metrics kind of internally in their own development of algorithms. Yeah?
I've heard some people mention kappa. How does that fit into this?
Kappa. I actually forget which one kappa is. Does anyone know how? I'm not sure. Specificity is kappa?
Correlation coefficient is evaluate a regression problem.
So
Kappa is very similar to that, which is in classification.
OK, so kappa is the correlation between essentially the correlation of this matrix here. OK, the correlation coefficient of that matrix, yeah. Yeah. So of the confusion matrix, it would be. OK. There's so many of these things that I admit I don't actually remember them all until you have to learn one for a specific domain that people care about. So the answer was that kappa, and I don't want to say too much because I don't know exactly how you said it, but essentially it's like a correlation coefficient for this matrix here, as opposed to for a matrix that for a more standard kind of linear regression problem. Right, which would apply to this confusion matrix here. Yeah. OK, so the last thing I want to mention here is that these false positives and true positive and false negative and true negative, they all assumed some threshold of making a decision, calling something positive and calling something negative, right? But we might, and in the sort of description of the actual algorithms, I set that threshold to be 0, right? So I said, if our hypothesis function is greater than 0, we predict positive. If it's less than 0, we predict negative. But why did we pick 0? Right? Well, it's kind of nice. It's sort of the obvious thing you would pick. But depending on the actual use case, I may want to use a different threshold that's not 0, right? Because I may have a task where I build my classifier, but then when I deploy it, I want to be very careful. I want to make sure I sort of catch as many of a certain class as possible. And so I'm actually going to use a different threshold and essentially maybe only predict negative if I'm really sure, really confident it's negative. And maybe if it's negative 10 or above, I predict positive. So this leads us to another set of kind of metrics we can develop based upon moving this threshold back and forth. And the key idea here is that it's not like we can actually achieve any possible classification by moving that threshold, right? We can never, and I have an example in the next slide, but the idea is we're going to actually sort our predictions by their hypothesis score. Okay, so if I have one prediction that is a negative 10 and one's a negative 8, there will be no rule that predicts the 8 to be negative, but the negative 8 to be the negative class, but the negative 10 to be the positive class, right? I can predict them both negative or both positive by adjusting my threshold, but I can never predict kind of out of order or the sorted order. So I'm going to sort them, and then I'm going to look at what my threshold looks like, or what my classification performance looks like at all possible different levels of that threshold. Right? And once we do that, we're going to evaluate various metrics on these different levels. So for example, say I have 10 total examples and maybe 5 total positive ones. And here's my sort of sorted list. So this is the most positive examples on the top there. If I think about the null set here, so I'm predicting nothing to be positive. I actually have no false positives either, right? Because I don't have any false positives. There's nothing that I'm calling positive that it's actually negative. I'm not calling anything positive. But actually, I have no true positives either. So my false positive rate and true positive rate are both 0. If I start now stepping down this list, right? If I look at the first element, now I have a true positive rate of 0.2 because I have 5 total examples, and I'm calling one of them positive. But I have 0 false positives, right? Because I'm not calling anything that's actually negative positive. So I have 0 false positives, but 0.2 true positive rate and a 0.0 false positive rate. And I can keep doing this. If I step down one more in this case, now I have I've actually classified that one as negative, or that one actually was negative, and I classified it as positive. So now I have still a true positive rate of 0.2 because I haven't gotten any more right. But now I have a false positive rate also of 0.2. And I can just keep doing this. So now here I have a true positive rate of 0.4 because I got another good true positive example, and still a false positive rate of 0.2. And so if I actually step through my entire data set like this, I will sweep out a space of possible combinations of true positive, false positive pairs. Right? Does that make sense? And if you plot that total set of combinations, you get what's called an ROC curve. Now, an ROC curve stands for receiver operating characteristic. I have no idea what that even means. It's some terminology from whatever domain that invented this, but just called an ROC curve now. And it is exactly a plot of all possible true positive and false positive rates you can attain from a classifier. So if I predict nothing to be positive, I'm down at this point over here, right? I have 0 false positive, but 0 true positives. I can always get that. It's really easy to get there, right? Not very hard. This point up in the top right here is the case where I predict everything to be positive. So I have 1.0 is my true positive rate. I'm classifying everything as positive as being positive. But I also have a 1.0 false positive rate because I'm calling everything positive. So both those 2 points are not very good. The point up in the top left corner there is kind of the best point you can reach in some sense. That would be the case where I have a perfect 1.0 true positive rate, but a 0 false positive rate. So that's perfect classification is up in that point over there. And by computing all these true positive, false positive rates and plotting it, we can kind of see how close we come to that spot in the corner there. This is actually for the cancer data set. I took, I think, the RBF classifier, and I plotted all the possible true positive, false positive rates. I didn't include actually I'll update this to actually include the line you can use from scikit-learn to do this, because it's actually quite easy to just, it's one line of code to do this. I'll add this to the slides next time. I realized I just saw it wasn't there. But basically, you can sweep this whole thing out, and the closer your line is to that top left corner, the better it is. But the way that the curve looks, sort of the actual sort of steepness of the curve can also really be important, right? Because it may be that for some cases, you really just want to make sure that I can get, some subset of true positives while getting very, very low false positives. Maybe that's sort of the desired case. While in other domains, you really want to be able to get all the true positives and see kind of how far down you can push your false positive rate by getting all true positives. So this is sort of a good way of looking at performance, especially when you have unbalanced data or data with different misclassification costs. But it's not a perfect metric either, because sometimes you really sort of care about only certain regions of this space that aren't really very well captured by the whole curve here. People will frequently, though, use the area under this curve as kind of a generic metric to capture how well the classification is working, though that can sometimes be a little bit unintuitive what that area actually means. And then the last thing I'll say is, again, sorry for not having the code here because it's actually quite straightforward. The last thing I'll say is we can also perform similar operations for other metrics. And so another very common one is to evaluate precision versus recall. So ROC curves evaluate false positive rate versus true positive rate. This is different from precision. There's no sort of notion of precision there. Whereas a sort of another common curve to plot is called a precision recall curve. Here you vary your threshold and talk about different levels of precision you get at different levels of recall. One sort of thing to note is that unlike the ROC curve, this is not monotonic, even though it looks like it here. But those lines are actually going up a little bit because the precision will actually decrease and then starts to increase actually until you make another mistake, and then they have sort of like jagged pattern. Don't worry if that doesn't really make that intuitive right now. But just know that these curves are not monotonic, unlike the ROC curves. Yeah? Yeah. So the question was, if we look at the ROC curve and then decide, I'm going to pick that point there, and that point associated with some threshold. Yes, that would be another hyperparameter. And so you'd want to pick that on a cross-validation set, and then evaluate whether you get the sort of desired true positive rate, false positive rate on your true test set. Okay, so I am getting a little bit over time here, so I might skip over. If you have questions on this, I went through this fast, and this was not meant to be that detailed. It was meant sort of to point out that there are these other metrics for classification. If you have questions, by all means, come ask after class or chat with me at some point. Okay, so let's jump forward now, because we're going to have now a lot to get through the next 2 days in probability. So, any sort of pressing questions there that are very fast? All right, I'm not going to give people time to change their minds. Okay, so now we're going to switch gears a little bit and talk about probability and statistics. And this is going to be hopefully a review for most people. We do sort of ask that there was, or we did strongly suggest that you have some probability background when taking this course. So hopefully this will be kind of intuitive to everyone. If not, we can suggest some other resources to look at. And going through the notes is very valuable, but it's probably by itself would not be sufficient to learn probability. And so we're happy to sort of suggest other resources to take a look at as well. Okay, but let's start by talking about probability in data science. And then we're going to talk about some basic rules of probability. So these are sort of things like marginalization, conditional probability, sort of basic rules that I'm going to cover very, very fast, because hopefully you've seen them before. And the thing I'm going to stress actually more than anything is the notation that we're using here, because I think that sometimes the most confusing point of probability is actually just the notation and what people actually mean when they write P of X. Does that mean a function? Does it mean a number? What does it mean? So I'll highlight that a lot. And then I'll cover, probably not today, probably tomorrow too, or Wednesday too, cover some common distributions. And then definitely next time talk about maximum likelihood estimation and naive Bayes. All right, so let's jump in to just sort of a high-level overview of, where's this? Yeah, probability in data science. So you may have noticed so far something kind of strange, right? That I've talked now for 4 lectures about machine learning and never mentioned probability. Which I think is actually okay. I think actually you can cover a lot of machine learning without covering probability, right? Machine learning is about minimizing loss functions. It's about specifying your hypothesis, specifying your loss function, and specifying an optimization procedure. There's no probability there in any of that. And in fact, a lot of algorithms, like support vector machines, really, you can try, but they aren't really probabilistic in sort of fundamentally. They are actually just sort of algorithms that are, optimization based, and there's no great probabilistic interpretation of them, I think. Though you can kind of put one on over the top if you really want to. But at some point, this is not going to be the case anymore, and we've reached that point now. Because, of course, understanding probabilities is kind of key to understanding data. And for the sake of this class, at least, for these lectures, I'm going to differentiate between statistics and probability in the following way. So statistics is, you can think of it as probability plus data, right? Because probability is itself is kind of a mathematical subject, right? It's about sort of the mathematics of random variables and how we take expectations and compute distributions, whereas statistics is about how you apply those things to data to actually make inferences about what's going on. Okay, so that's the line I draw there for those that are curious about that point. But of course, both these things are hugely important to real data sets and of course to data science. To the point where we even actually had a little bit of probability already when we talked about language models, because we just couldn't get away from it. But now we'll treat it in a little bit more depth here. And the rationale for this in some sense is that there are many domains at the level that we're going to ever have data that are fundamentally uncertain on some level, right? Maybe they're not, at the atomic level. If you get down to the quantum level, things are deterministic. I don't even know if that's true or not. But if you don't do that, there are certain processes that as far as we are ever going to be able to have data for, there's going to be uncertainty there. So let's take this example we had last time of predicting peak demand from high temperature, right? There are ways to decrease this uncertainty a little bit, as we saw, right? We can also add things like the day of the week, etc. But these are fundamentally a human produced data here, right? Humans decide to turn on the lights or not. So I could go over, assuming that I have free will, right? I could go over to the lights and turn it off, and presumably no algorithm could have predicted that from yesterday or even the high temperature today, whether I decide right now to go turn off the lights or not. And that's going to affect, of course, the total demand that we use in Pittsburgh today. So there's going to be some uncertainty around this. And you can see this in the data we already have, right? Where if you take one high temperature here, there's a spread of possible power people actually have used that with pretty much that exact same high temperature. And so it's important to really understand this data. It's important to go beyond just sort of drawing our line through the data and saying that's our prediction. We also want to quantify how uncertain we are in that prediction, or kind of model the probability that we think for this high temperature it's going to be this much, or it's going to be this much. What's the chance of that event happening? Of course, this is just one example, but there are many, many domains in which we really want to be able to sort of the answer that we're looking for is not just a prediction. It's not saying negative is this one. It's the answer actually is a probability of how much we think this is, say, a malignant or a benign tumor, which may be much more important than just saying yes or no, right? So that's kind of where probability comes in to data science. I mean, one of many ways in which probability comes into data science, but also I think necessitates something beyond, even in machine learning, beyond just making sort of point predictions. So I've seen a lot of people say, work on some task, and then they get, a classification task with 50 classes, and they get 70% error, and they say that sounds very bad, or 50% error, right? And that sounds very bad, but actually, sometimes that is as well as you can possibly do, and understanding your task not just as a number of accuracy, but actually in terms of how well can you capture the true underlying uncertainty in your data is the most important element here. So with that being said, let me really rush through the rules of probability now. And I'm going to do this very fast. I'm not going to get through it all today, but I will. We have 15 minutes left, but I will try to get through a lot of it. And so it's going to be very fast. If you haven't seen this before, please let us know. We can point you in some other resources, because this is going to be very, very quick. But I'll highlight what I think are the most important elements here. Questions before I start? All right. Take a deep breath. Random variables. I'm not going to define random variables formally in terms of functions or probability spaces, anything like that. I'm just going to call random variables a variable whose value we don't initially know. Right? They take values in some set. So for example, the weather random variable could take values in sunny, rainy, cloudy, or snowy. And each of these possible outcomes is associated with a probability. These probabilities are numbers. They're between 0 and 1. And the probability for all possible outcomes has to sum to 1. Right. Hopefully that much is well known to everyone here. We're going to use a little bit different notation with continuous random variables, but I'll get to that shortly. OK, so in this lecture, I'm going to use uppercase letters. And I'm going to only promise this for this lecture. I may deviate from this for future lectures. In fact, I certainly will deviate from future lectures. But in this lecture, I'm going to use uppercase letters to denote random variables. And I'm going to use lowercase letters to denote the values that random variable takes on. And this is actually really important when we talk about what I mean by an expression like this. So what do I mean by p, little p, of big X? The other unfortunate thing is that when I write little x and big X, you can't really tell the difference, but it'll be in the slide, so hopefully you'll know what I'm talking about. When I write p of big X here, what I mean is the entire distribution over the random variable x. So the way to think about that is you should think about that as a kind of like a dictionary mapping the values that this random variable can take to probabilities, right? To the numbers. So this thing, what I mean really, and say I have a random variable with those values, what I really mean, kind of, and I'll actually even write it more than this, what I really mean here is that the value 1 has probability 0.1, the value 2 has probability 0.5, and the value 3 has a probability 0.4. That's what I actually mean by P of big X. In comparison to that, by P of small x, I'm going to try to exaggerate those when I write them, but that's P of small x. What I mean there is a number. Right? That is the number for this value of x. And I can also write this, for example, as P of big X equals 1. In this case, little x is equal to the value 1. But it's very nice sometimes to not have to write all the actual values out. And so the little x's will refer to values that the big X can take on. In this case, it would be 0, or it would be 1, 2, or 3. Right, so this is a placeholder for the number 1, 2, or 3. OK, now that actually is the hardest part of probability, honestly. Keeping those things in mind, at least introductory probability. There are a lot of people, I think, that take a course in probability and sort of learn all these rules. When they actually have to implement it in code, this distinction actually gets lost sometimes. And it's a very important distinction there between these two things. So make sure that's sort of in your mind the whole time when you think about these variables. OK. So some quick examples here. If I have two random variables, x1 and x2, with x1 takes values of 1, 2, 3, x2 takes values of 1, 2, then P of x1 comma x2 refers to what's called the joint distribution. So P, and these are big x1 and x2, refers to the joint distribution. This is the probability of every possible assignment to x1 and x2. And because these are big variables, what that really means is this is a mapping, a dictionary, from all possible inputs. 1, 1 to some probability, 1, 2 to some probability, etc. It is a dictionary mapping all possible settings of x1 and x2 to a corresponding probability. Similarly, P of x1, x2 with little x1 and little x2 is just a number. That is the number, that is the probability for that assignment of variables. And again, this is going to be, I know this seems kind of trivial right now, but it is actually a point of a lot of confusion sometimes. I can mix and match these things too. So I can also write things like P of x1, comma, little x2. And what that means is that is again, a dictionary over all possible values of x1, because x1 there is the only big random variable. x2, on the other hand, is a fixed value. So what that means is for that fixed value x2, what is the entire distribution over possible x1s? All right, so it's going to say for x1 being this number, this value, the probability of something. For x1 being this value, it's probability of something, etc. Now, importantly, this distribution here is not really a distribution at all, right? Because this will not sum to 1, these probabilities here, because this guy is fixed. So it's only counting half the possibilities if that has two values, or potentially much fewer. So these sort of, whether or not something is really a distribution will depend on, are the values fixed or not, or we'll see some other examples of things like conditional probability, which are, strictly speaking, not actually distributions in the sense that joint distributions are. And so because of that, we're going to have a name for these things. We're going to call these generally factors. So a factor refers to any combination of a full distribution where some of them have been set to certain values and you have distribution over the other ones, or even you can call a factor just the actual number, but that typically we just call it a number, but it technically actually is a factor as well. And so all these things are called factors. And then finally, we can perform operations on probabilities or factors by essentially looking at the variables themselves, the big X variables, and computing a number for all possible settings of those big X variables. Okay? So what I mean by that is the following. So if I have, I actually did not use this board very efficiently here, but if I have some factor, they could be distributions or not, I don't actually care. If I have this and I want to apply some operation of this, this is sort of any operation, addition, multiplication, whatever. Addition actually is a little bit different. Think about multiplication maybe, but addition, you have to have some other conditions too. But if I have something like this, so think of this as like multiplication or division here. What I mean by this is that this is an expression that has 3 random variables in it, right? x1, x2, and x3. So this whole thing is a factor over x1, x2, and x3. So what it's going to be a dictionary mapping assignments to x1, x2, and x3 to actual values. Okay? Now, if I want to know what is the value for a given setting of x1, x2, x3, well, I just look at the actual little x1, x2, and x3 and compute that. So I just would compute p of little x1, x2, whatever my operation is, x2, and x3. This is going to be the most unintuitive board for someone not unable to know the difference between my big x's and little x's. But basically, does that kind of make sense? So these look very, very similar, and they unfortunately follow a lot of the same rules too, so people kind of use them interchangeably. But this one here is a actual factor that says for every possible setting of x1, x2, and x3, this takes on a certain value, whereas this one says, you know, for this and what that value is given settings. So you know, I can always use this notation like this, right? Given x2, x2, x3. The value of that factor, when I plug in some values, would just be the corresponding factors multiplied by each other for those values, right? So this is a factor, it's a dictionary, whatever you want to call it. This is just a number. All right, so that's actually probably the hardest part of probability. Once you kind of see that, everything else becomes pretty easy. Because then it's just kind of rules, and this is just kind of math after that. I'm exaggerating a little bit. It isn't quite that easy, but that is a really confusing point. Speaking of which, I should pause and ask if there are questions about that really confusing point. Is this familiar to everyone? This kind of discussion here? Okay. All right. So now let's jump into the actual traditional rules of probability. And I'm not going to drive from first principles. You know, I'm not going to sort of talk about like the union rule or these kind of things. I'm going to talk about the practical rules people actually use of probability. And those are the following. I think they're the following. The first one's going to be conditional probability. So the conditional probability of p of 2 random variables, p of x1 given x2. We said this is the probability of x1 given x2. This is equal to the probability of x1, x2 over probability of x2. Okay? And now that we know our rules, we know what this means, right? This thing here is a distribution. It's actually not a distribution. I take it back. It's a factor that for all values of x1 and x2 will provide some number. The way I get that number is I take my specific value of x1 and x2, plug it in here, then this is a number here, and so I get that number. But this and this side are both factors. They're both actual dictionaries from assignments to values. Now, importantly, this one here will not be a distribution, right? Because it will not sum to 1. These terms will not sum to 1 if you add them. You know, all the terms here will not sum to 1. They will sum to 1 in some order. So if I look at, you know, given a fixed value of this, that is a probability distribution then. But that's sort of the way it's going to work. This here is still a factor. It's still a it is still a dictionary from mapping from assignments of those variables to a number, but it is not, strictly speaking, a distribution. It's a conditional distribution, which says that for a fixed value of, in this case, x2, that would be then a distribution. So p big X1 given X2, that's a distribution over X1, where X2 is little guy now. This can also be written, and often is written, by moving this guy over here. So take this from that side. Where did my eraser go? Take this from this side and put it over here. The way this is normally read is the other way around. So P of X1, X2 equals P of X1 given X2 times P of X2. And this generalizes even more to what's called the chain rule. So if I have a whole sequence of random variables, then the probability, the joint probability over all the random variables is equal to the product of conditional distributions of, if I have some ordering, say, 1 to n, it would be the P of x I given all the variables that precede it in that ordering. The ordering can be arbitrary, though, of course. You can do it whatever order you want. That's called the chain rule. And all it is just a repeated application of this rule right here, this definition of conditional probability. Oh, did I write big P by mistake? I should never write big P here. Big P is nothing. Let me fix that. People use big P. They will often sometimes use big P for discrete variables and little p for continuous variables, but I'm not doing that. They're all little p here. Okay, so next rule we have in our sort of toolkit is called marginalization. So if I have a joint probability and I sum over one of the variables, so if I take P of x1 and x2, but I sum over all the possible assignments to x2. So this is a big x1 and a little x2. This is equal to the probability of x1. Sorry, this is big x1 here. It's much easier to read than to read decipher which of mine are big and little variables there. So go by this here. And this, by the way, is also equal to, we can use our same rule of conditional probability here. Say this is also equal to the sum over all x2 of P x1 given x2, sorry, big x1 given x2, P x2. Where again, little x2 is a number. This is a distribution of all values that x1 could take on given a fixed value of x2, but then we're summing that over all values of x2. And by the way, if you marginalize out all variables, you should always get 1 for distribution. That's kind of the definition. The things have to sum to 1 when you sum over all possible assignments to it. Okay, questions there? Yeah. Yeah, so actually this is important. What I mean by this, okay, so what I mean by this expression, sum over all x2, is I am summing over all values that the variable x2 takes, and I'm calling that x2. So if, for example, x2 took on variables 1 through k, then this assignment here would be the same thing as saying basically for x2 equals 1 to k. Okay, it is implicitly summing over all possible values that x2 can take on, namely the values that the variable x2 has. Okay, so if the set of values it could take on was 1 to k, this would be the same as saying the sum from x2 equals 1 to x2 equals k. Okay, that's actually a really good point. Because I'm gonna use that a lot actually, that notation there. So the sum over some x2, or sum over x anything, means I am summing over all possible values that variable can take on, and I'm having one essentially iteration of my sum for each possible, where it takes on each possible value. And I mean that for here too, right? Here what I'm saying is, I'm going to sum over all possible assignments that all the variables can take on, and I'm going to compute that number of probability that has to equal 1. Here I'm going to compute the sum over all possible values these remaining variables can take on. I'm going to compute that probability there. Okay. We're going to have a lot to cover next time, but we'll cover it fast. And we'll talk about Bayes' rule starting next class.